the seminar. So today we have Andreas Tamosiunas. I hope I spelled it somehow right. And he's giving us a talk for us today on how investigating screening mechanisms using numerical methods. He's at University of Nottingham. So thanks a lot, Andreas, for accepting the invitation. And whenever you like, you can start sharing.
All right. Okay, so hopefully you can see that. Let's see. It's blocking my.
Could you fix the screen, please?
Yeah, sorry, this thing is just kind of blocking my.
Move it up a little bit, the projector screen. This?
Yes, it's
Oh yeah, yeah, I see. What other way?
Yeah, but probably needs to be turned down.
Maybe a gentler type.
Probably need to like get it all the way up to put it down again.
Usually it seems to come down and it goes up, right? Gently, so.
I mean, I don't know. I've never used it before,
I do feel
so
sorry
I was
about
just.
watching the cut.
Yeah, that's definitely much worse than it was.
Is there a... It's not motorized, is it?
No.
No. Maybe we should-
That's all of the wrist action.
Sorry.
No.
Sorry.
Everything's sorted now. Looks
I swear I thought I did the same thing.
Okay, so hopefully it's all good now. Full screen.
Yes.
Yeah, thanks to Tim, yeah.
Okay. So, hi once again. The topic of this talk is basically, as mentioned, numerical studies of screening mechanisms. In particular, we're going to be focusing on FEM, which stands for the Finite Element Method. And this is some of my recent work, but obviously also the work of my collaborators who are listed here from the University of Nottingham. And as you might kind of guess from the colorful picture on the right, one of the models that we're going to be focusing on is the Chameleon model, but not only that model, but perhaps let's start at the beginning. So let me just say a few words about modified gravity. It's obviously a talk about different kind of modifications of GR. So, what is the case for modified gravity? Why are we interested in that? So obviously from kind of the cosmological side, the two big problems are dark matter and dark energy. And by modifying general relativity, we might kind of get some clues about, what is the nature of these problems. Another obvious reason is quantum gravity. We know that GR is incomplete to some extent. So obviously, once again, kind of breaking various assumptions, modifying GR, we might get some clues about, the theory of quantum gravity. But just from a more philosophical standpoint, I think to really understand how gravity works, you kind of need to build different theories to kind of take them apart, build them back up with different assumptions. And I think this is just for the kind of theoretical curiosity, it's a good reason to look at these types of models. And there are, of course, all kinds of different models which break different kind of tenets and assumptions in GR and have different phenomenology on different scales. So there are many different classifications that you could come up. Here's one probably oversimplified classification, but just to kind of give you just a rough map of some of the different models that we have. Now, in this talk, we're going to be focusing on models that have screening mechanisms. So perhaps the most well-known example, or one of the most well-known examples, is the Chameleon Gravity model. It's a scalar tensor theory with non-minimal coupling. As you can see, it kind of looks, you have the GR part in the action plus an extra scalar field with a particular potential that we're going to be kind of looking into in a moment. And a particular coupling that's defined here in the matter-Lagrangian part. So the equation of motion, if you vary this with respect to the field phi, you get something like that for the equation of motion. It's nonlinear. That's one of the key points here. And even if you simplify it and say, okay, let's take the time-independent case and the non-relativistic matter, you still get something that's nonlinear. And in fact, it's difficult to solve in most of the cases, except for the very kind of simple symmetrical cases like spherical symmetry, cylindrical symmetry, and so on. But the main point is that to really kind of describe the physical system, you need to solve this equation of motion, and that's usually difficult to do. Now, a few more things about chameleon gravity. So actually, if we go back to this equation of motion, if you can see these terms, two terms on the right-hand side, it turns out that we can kind of define an effective potential that's basically just equal to the potential V of phi plus these extra terms that depend on the density. And it turns out that the behavior of this effective potential kind of describes most of the important kind of behavior of this model. So in the high density regions, this is the shape that the potential has, kind of this nice parabolic shape where the field is just stuck and it does not propagate. And we say that basically it's screened. So the fifth force is very small, well, practically zero in those regions. But in the low density regions, the field propagates, the fifth force is not very small, it's not equal to zero, it can be much larger. So the field is said to be unscreened. And this interesting behavior allows us to satisfy the solar system constraints while potentially having still some interesting phenomenology on larger scales. And perhaps quite unexpectedly, it turns out that there has been a lot of work showing that you could still have very interesting phenomenology on smaller scales, even in laboratory experiments where you would think that the density is very high. But it turns out that by kind of playing around with, let's say, vacuum chamber experiments, you can actually test a lot of these models. And we're going to have a look at that later on. So the next example, just very briefly, is the Symmetron Gravity. So it's another example of a screening mechanism. So the key difference here is that we basically have a different potential. So it's still a scalar tensor theory with a different potential that actually has this interesting shape that you can see here. So for high density, once again, this type of a parabolic shape. And then as you kind of decrease the density, it undergoes this kind of a phase transition with two minima. And basically, it has the same type of a similar type of a screening effect, such that in high density regions, once again, the fifth force is screened. The modified gravity effects are kind of suppressed, and in low density regions, you could still have interesting extra force and interesting kind of phenomenology. Once again, in this case, an even more difficult equation of motion that is difficult to solve. One other thing I mentioned here is that this type of a potential can actually lead to interesting topological defects that I'm going to discuss later on. But the main point, the main key point that I wanted to kind of emphasize here is that solving these equations of motion is complicated. Generally, numerical techniques are needed, and there are many different approaches. So I just mentioned a few approaches here, just kind of general classes of approaches. But the one we're going to be focusing on here is the so-called finite element method. And this kind of a diagram here or picture here illustrates the kind of a philosophy here that we split our domain into these little parts called the finite elements. And in each of these little domains, we solve a particular version of the equation of motion. And then we kind of join all those solutions in a smart way to satisfy the boundary conditions. And in this way, you kind of obtain an approximation of the solution with usually a very good accuracy. So that's basically the model, the technique that we're going to be using. So yeah, part two, the finite element method. So the finite element method is basically a numerical method to solve linear and nonlinear equations. Usually that's in 1, 2, or 3D. It is possible to do it in kind of higher dimensions, but usually people use it for up to 3D. It's widely used in engineering, fluid dynamics, structural analysis, and all kinds of different applications. And there are many software packages with different functionality. So how does it work, kind of roughly speaking, without going, into the very kind of hairy details and boring you? Well, you start by defining some domain. Then you discretize the domain into these little elements, the finite elements. You can have, different choices here. How exactly do you want to obtain this so-called mesh? Then you kind of approximate the function that you want to solve. Well, you kind of re-express it in terms of a sum of some basis function that you can choose, basis functions, and particular coefficients. These are the coefficients that you're going to be trying to obtain numerically. You kind of assemble the system of equations. So you take all those little equations in each of those finite elements, and you basically form a system of equations that you can solve. So this is where you can use various matrices and matrix methods to kind of make the solutions easier to obtain. You define the boundary conditions. Here you have a choice of kind of different boundary conditions, whether you set the value of the field to some value at the boundary, or whether you set the derivative as well to some particular value, and so on. And then you solve each of those little equations. And here you can actually use a variety of methods. This could be some classic methods like the Newton method, where you use the value of the function and or the derivative of the function at a particular point to find a solution, or the Picard iteration method, and so on. So this would be like a typical kind of illustration of a problem that you could solve with this method quite easily. So let's say you have a wire in this case, and you want to obtain the electrical field around it. So obviously a very spherical system, you kind of create a mesh, which is basically just discretizing your domain into these small triangular elements. And in each of these elements, you kind of find the values of coefficients. So actually in 1D, if you have some function u, you could approximate this function u as a sum of these coefficients ui and the basis functions, which are defined such that they're equal to 1 at a particular node. And at each node, actually, once you obtain the solution, it's equal actually to the function you're trying to find. But then between those points, you can actually interpolate. So it's not exactly equal, but depending on the mesh resolution, it can be very close, as it is the case in most of the kind of numerical techniques. So obviously, all that I mentioned, you don't usually do, well, almost none of this by hand. There are various software packages that you can use. That includes Phoenix. So Phoenix is a software library for essentially doing the finite element method analysis, so all that I just described. It allows kind of automating the mesh creation in 1, 2, and 3 spatial dimensions, automatic discretization, obviously, and it allows for various methods to solve linear and nonlinear equations. And obviously, there's all kinds of applications once again. So this is from last year's conference in so the Phoenix 2021 conference. And this is just some examples, anything from kind of describing the, I guess, the blood flow in the chambers of the heart, to various fluid dynamic applications, to kind of modeling neuron activity. Obviously, in this case, the key point of this talk is basically that we're going to be using that for solving the nonlinear equations of motion in modified gravity. So I mentioned an example already, but here's another simple example. So let's say you want to find the deflection of a 2D membrane when you apply some load on it. So basically, you have a drum, let's say, a 2D drum. You put some weight on the drum, what's the deflection? So a very simple equation. Actually, if you look at this equation, T is some tension here, but basically this has the same, almost the same, what is the same as the Poisson equation, pretty much. And if we assume the load to be some Gaussian function, well, this is what we usually do is, okay, we first of all rescale the equation just for kind of simplicity. So we rescale the deflection by some characteristic deflection. We take all the different constants that appear and we kind of gather together all of them together on the right-hand side in this parameter alpha. And this is what we have. So then we can use Phoenix to basically transform this to a variational form, which is just kind of multiplying both sides by a test function, which doesn't really matter the shape of this function because there's like a theorem that says that, you know, it should work for any form of this function. And then you use Green's function, or basically just kind of integration by parts to express it in a variational form. You discretize the domain, which Phoenix does that for you automatically, and you solve this via Picard iteration or Newton method or many of the other methods that you have. And you obtain something like this. So this is our domain in 2D. You can see the mesh superimposed on that. This is the load. So basically just putting some weight on it. And on the right, we have just the solution. So the kind of deflection of the drum in this case. And I mentioned this example because basically, as we're going to see, it's very similar to the modified gravity example, besides the fact that it does not have the nonlinear term. But the equation itself is just a modified version of the Poisson equation. Okay, so that's the end of part 2. So now we're going to look at our code specifically that is specifically dedicated to solving the modified gravity equations. Okay, so the code is called, following the traditions of bad acronyms, it's called Selkie. Which stands for Screening Equations Linearly Constructed and Iteratively Evaluated. But the code itself, well, the word itself, Selkie with a K, actually stands for this mythological creature in kind of Nordic mythology specifically, which is half seal, half man or a woman. Just to kind of give you some trivia there. But it's basically a wrapper around Phoenix with some extra functionality dedicated to solving nonlinear equations of motion and modified gravity. So at the moment, it's optimized to solve equations in 1, 2, and 3 dimensions. So we don't have time dependence yet, but we're kind of working on implementing that at the moment. It has automatic mesh creation. Using something called Gmesh. And I should say this is on Python, so this is a Python implementation, but Phoenix itself also has C implementation, C++. So I have this link here to the GitHub repository. So I'm going to show that in the end, just in case you're interested. But basically, the key point is that if you go to that GitHub repository, there's a bunch of example codes which kind of run through some simple examples, and they're quite well documented. So I will not go into the very details as to how the code works, but obviously, if you're interested, you can go to this GitHub repository and test it out yourself. Or obviously just kind of email me or Chad Britton, who's one of the key developers of this, a PhD student in Nottingham. So yeah, if you just contact one of us, we'll be happy to help. But probably the best way to look at some of the results is to look at some simple examples. So what happens for when you define a symmetric source? So let's say a sphere, or in 2D, a circle, or a something with cylindrical symmetry. So basically, you can obtain this very easily. And here are some solutions compared to the approximate analytical solutions, because we know that for a sphere or for a cylinder, we know the analytical solutions. And this is done for a very small source in this case, so something like 0.05 times the size of the domain. So this is all normalized by the size of the domain. And the field is normalized by the background value of the field. Just to see basically if we have some weird numerical artifacts on very small scales that would mess up the solution. But it does not seem to be the case. The solution, as you can see, agrees quite well with the analytical solution. And obviously, as we're later on going to see, we can look also at elliptical sources. We can look at all kinds of different sources with this code quite easily, which is very much of interest because as some research shows, in particular this paper by Burridge and others from 2014, ellipticity, or essentially in generally changing the shape of the source, can have an effect on the screening mechanism in chameleon gravity. Okay, but that's quite simple. We know the analytic solution, so that's not very interesting. A slightly more complicated system that's already quite interesting and realistic is essentially modeling a vacuum chamber. So how does this work? Well, vacuum chamber experiments look for fifth forces using interferometry. So a typical setup would look something like this. You have like a vacuum chamber that has a particular sphere made from some metal, usually in this case it's aluminum sphere, with certain atoms, in this case cesium atoms, falling towards that sphere. And basically using this laser and mirror setup, you can actually measure the acceleration of these atoms very accurately. And the logic is if there's like an extra force, an extra fifth force, you can in principle detect that, or at least put some boundaries on the size of this force. So if we actually model that in our code, it looks something like that. We have the vacuum, we have the wall, the source. You can see the mesh here. So this is just the density distribution here, basically. And you just solve that with the code, and this is the solution you get. This is the field profile, rescaled once again by the vacuum value in this case. Yeah, so obviously this is a very, once again, still a very simple system. Now you have the walls, but it's still spherically symmetric. So actually a more general question is, what would be the most optimal source shape to maximize the fifth force in these types of experiments? So let's say we have something completely arbitrary. Well, in this case, it's we generated this using Legendre polynomials, some very complex, complicated shape. You can solve, you can find the field profile for that quite easily with our code once again. So actually, one of the questions we're tackling with Chad Burden, who I mentioned recently, one of the PhD students, is what would be the most optimal shape? And we're using genetic algorithms to figure out, what would be the most optimal shape to maximize the fifth force at some distance from the source. Yeah, so obviously this is more interesting in the sense that, well, there's no way you could find a solution for something like that analytically. So this is where the kind of usefulness of numerical methods come in. Okay, another example, NFW Halo. So now kind of switching gears, going into kind of the domain of cosmology now. So dark matter halos can be described by the so-called NFW profile, which just tells you the density at some radius r. So it has two free parameters, that's either rho naught or rs, or equally the same, you can express it in terms of the virial mass and concentration. It looks something like that in 2D. And once again, we use our code and we get the solution for the field inside the NFW Halo profile. Obviously, this is all spherical. Real NFW halos, or real halos, I should say, in nature are not exactly spherical, but you can easily switch to, let's say, triaxial coordinates, where you just divide each of the Cartesian coordinates by some parameter, QA, QB, or QC, and you can describe triaxial NFW halos, where it's kind of stretched or squished along each of the axes. So before moving on and just doing a more general analysis, just to kind of test what size of the fifth force we can get in cosmology, let me just tell you a few things about the current chameleon constraints. So as you can see from this picture, it's, well, almost entirely ruled out, unfortunately. So not a lot of interesting not a lot of interesting regions in the parameter space. So all the colored areas are ruled out. The dashed line here is the dark energy scale. So these are the models that would give you some interesting phenomenology in the context of dark energy. There's a very little triangular area here that's not yet ruled out by interferometry. But basically, just by kind of trial and error, we found out that basically the best surviving models in terms of the fifth force size are, well, it's this triangular region here. And this is simply because the fifth force depends on 1 over m. M is the coupling here. So we want that to be as small as possible. Or actually, well, basically we want that to be as small as possible here. And we want n to be also close to 1. N, once again, is just one of the parameters in the Chameleon model. So these are the regions that we kind of focused on. And then we've done a more general analysis. So we've taken data from the so-called 300 project simulations. So this basically refers to a simulation suite that simulated using hydrodynamical effects 324 galaxy clusters with kind of realistic physics, combining semi-analytical models with hydrodynamics to basically paint like a very realistic picture on galaxy cluster scales. So we've taken all those halos and we kind of ran our code on them. And this is the result that we get. So we have the virial mass of each halo, the concentration of each halo, and the color is basically the ratio of the Chameleon acceleration versus the Newtonian acceleration at the virial radius at each halo. So what does it say? Well, first of all, these numbers are very, very small. So basically it's saying that, the Chameleon force that's still allowed by the constraints is just really, really small. And most likely, even if it exists, it would not have any significant effect on cluster scales. Because remember, these are all kind of galaxy cluster scale halos. We actually ran that incidentally on kind of smaller, different halos. And actually, if you have some very small galaxies that are that the density is very low, you could still actually get some significantly higher numbers there, but still probably quite difficult to detect observationally. Now, another question that we can ask, because in the simulation data, we also had the shape information for each halo. So these are the so-called triaxialities of each halo. So what happens if you take into account the shape of each halo? Maybe that kind of helps us out with, increasing that fifth force. And actually, triaxiality, just to mention, has a few different effects. So as mentioned, just by having elliptical or non-spherical sources has an effect of reducing the Chameleon screening by a factor of, 2 or 3, something like that. But another effect in NFW halos in particular is kind of demonstrated here. So each dotted line is basically a different value of the density. And if you measure the acceleration, let's say along the x-axis and the y-axis at the same distance, whatever it might be, it's going to be different just because of this distortion of the NFW profile by the triaxiality or the ellipticity of the halo. So this could potentially be useful in, detecting these types of effects by kind of, if you could measure potentially, if that's possible, whatever the force effects or the acceleration in some sense, perhaps measuring the pressure of the gas in the cluster along the kind of y-axis, let's say, and the x-axis, you could potentially gain some insight about the size of the fifth force. So once again, we take all those, the same 324 halos, we run our code on it. This is what we get. Just to remind you, QA and QB are these coefficients that tell you how stretched the halo is along the x and the y-axis. By definition, if it's equal to 1, that's the spherical case. If it's not, then it's either stretched or squished. So the main point is that these are the spherical halos, and the more you move away from that diagonal, you have the non-spherical halos. And the color now is basically this difference between the acceleration along the y and the x-axis. So in the most extreme case, in the most triaxial case, this could be up to, let's say, 50%. So if you could potentially measure something like that, obviously this would be a great effect to look for. But once again, we go back to that fact that the force is very small either way, because most of the interesting parameter space regions are already ruled out. But anyway, obviously the full results are given in more detail in this paper that kind of studies these types of effects. Okay, so the last example, and this is what we're kind of working on at the moment, is cosmic voids. So cosmic voids have been shown to also, to some approximation, to follow a universal void profile. So there are a couple of choices here, as it is the case with the dark matter halos, but this is one possible choice for the void profile. It looks something like that. So these are different density profiles for different depths. And the dashed and the dotted lines here correspond to some realistic void profiles that were fit by running simulations and using actual observational data. So I think this is the Navitur one is from SDSS and simulations, I believe, and the one from Chantivat and others from 2017. I think this is using CMB lensing data and simulations, I think, as well. But this is just some indication just to give you an idea of what a realistic void profile would look like. So once again, we obviously put that into our code and we want to calculate the corresponding fifth force or acceleration ratio profiles. So this is how it looks like. So what you're seeing here is basically we take those void profiles, and in this case, we vary the delta C parameter, which controls the depth of the void. And what this is saying is that, as you can see, there's quite a few lines here, but what this is saying is that the deeper the void is, the larger is, relatively speaking, the chameleon force or the chameleon acceleration inside, close to the center of the void. But basically, as we found, it basically follows, it's very much related to the shape of the density profile. Actually, if you compare this to the realistic profiles, as you can see, they have a slightly different behavior just because the inner kind of a gradient of these profiles is quite different. So that's also an interesting point. And basically, a lot of this can be actually derived analytically just because we are in the parameter region space where, so this is the equation of motion, it's rescaled. Alpha contains all the different constants in the equation of motion. It turns out that it's basically always very, very small. So we can actually approximate the field by the density raised to some power. So this is why you're seeing this kind of a behavior. Yeah, okay, and just a few more plots. So we're just varying different parameters here. So the alpha from the profile, the beta, and also one of the parameters, as you can see here, is the ratio between the scale radius, and this is the typical size of a cosmic void. So as you can see, we can get slightly different behavior depending on which parameters we vary. But the key point is that it all depends on the shape of the density, kind of as expected to some extent. Okay, and just to finish off, just a few more slides left about some of the future work. And well, we're already kind of working on the Symmetron case. Okay, so I mentioned the Symmetron model. Obviously, it's density dependent, as mentioned, which means that the effective potential changes shape with the density. So there's this interesting kind of a behavior that if you reduce the density slowly, it goes from one of these shapes, the blue shape, to the red shape. So it basically undergoes this continuous phase transition. And basically what happens is that the field can relax into one of these two minima, one of these two little valleys in the red shape of the potential. So as you can see, the values are given here. This is the potential. The two minima are given by the energy scale and the coupling parameter here. And basically such behavior, it's a classical behavior that shows up in many different areas of physics, but it leads to topological defects. So in 2D, this refers to, or 3D, to domain walls. So domain walls could in principle be detected in vacuum chamber experiments or even cosmologically. So what does it look like? Well, let's say we have a vacuum chamber. In principle, we could use this model to pin a domain wall between, let's say, these two, or I don't know, just the two different walls in the vacuum chamber. So you would start with some density, you would slowly reduce the density, and in principle, if obviously the symmetron exists, then you would get this type of a phenomenology of a domain wall appearing and kind of pinning to the two sides of the wall. And in principle, the way this would work is that if you add a test particle, let's say you shoot a stream of test particle to this domain wall, which basically all of this is just the area that kind of the continuous. So you have basically two values of the field. One is negative, one is positive. So it has to be continuous. So this transition region is just the area with the field gradient being quite high. And that's the domain wall in this case. So the test particle would basically feel that fifth force, and it would either propagate or would bounce back with a particular probability. In fact, for a 1D infinitesimally thin domain wall, you could calculate these reflection and transmission coefficients. So you would write down a Lagrangian like that for the matter fields and for the symmetron in this case. And you can actually calculate these reflection and transmission coefficients. But obviously for more complicated setups, numerical techniques are needed. So in fact, one of the issues if you want to detect these types of domain walls is that realistic networks of domain walls would have a much more complex time evolution. So it would look something like that. So once again, we have a vacuum chamber. We're reducing the density in the vacuum chamber slowly, and the symmetron would kind of result in these domain wall networks, basically. It would look something like that, but it would not be stable, and it would most likely decay to something like that. So yeah, generally these walls are not stable, and stabilizing them has been a question in the literature. Actually, one thing you can do, as discussed in this paper by Pearson, is you can actually introduce extra density sources inside your vacuum chamber, or cosmologically, you could have, let's say halos inside a cosmic void or something like that. And then you can show that a domain wall, which is shown here by this ring, could essentially pin to these different networks of circles in this case. So basically, by introducing these extra sources, you could, in your vacuum chamber, let's say, you could stabilize the domain walls, and then you could detect them. Now, obviously, a big question is whether something like that, in principle, at least, could happen in nature. So, for example, there has been this paper by Linares and Bogosian from 2014. They investigated the case of pinning the domain walls to cosmological filaments, cosmic filaments, and they've shown that at least in principle for some parameter space regions, it is possible. One question we're quite interested in is, so we know the case of the vacuum chamber, you pull out the air of the vacuum chamber, and you could in principle make these domain walls manifest. The question is, could you have something like that in cosmic voids throughout structure formation? The voids, basically the density inside the wall, inside the voids gets lower and lower. And in principle, for some parts of the parameter space, you could have a similar type of effect of such domain walls manifesting. The question, once again, even for modeling something like that with our code, is how do you stabilize these domain walls? One possibility is that you could have, let's say, different dark matter halos, because cosmic voids are not entirely empty, despite the name. So you could, in principle, pin these domain walls to the networks of these dark matter halos. So yeah, this is the last slide just to summarize the current state of the code. I talked a lot about the Chameleon code. At the moment, what we have is it allows you to solve the equation of motion in various scenarios. We have done quite extensive vacuum chamber modeling. We investigated galaxy clusters. And at the moment, we're investigating cosmic voids. So almost done, just kind of writing up at the moment. And one of the things we want to investigate next is time dependence. So what happens if you have an extra time dependent source or extra time dependent term in your equation of motion that would allow you to have more realistic simulations. Now the Symmetron, we managed to get it to work just quite recently. Still a lot of progress to be done for vacuum chamber investigations. And then we want to look at the same type of sources like galaxy clusters or galaxies, NFW halos, obviously cosmic voids, and ultimately we need time dependence to investigate these types of domain walls. What about Weinstein screening? Well, possibly we plan to implement it in the future. One reason we are not working on that at the moment is that there already is a code by one of our colleagues, Daniela Sadi, which you can actually find here. So it actually allows you to model using the same type of approach, the Phoenix code. It allows you to look at different Galilean models with Weinstein screening. But basically, I know I didn't go into too much detail about how the code works specifically, and this is mostly by design, because you can go to this GitHub repository and we have some nice documentation. We have the different examples for a spherical source, for a cylindrical source, for a vacuum chamber, for NFW halos. So yeah, feel free to explore that if you're interested. And obviously, if you have any issues, just send me an email. And yeah, that's it. Thank you very much for listening.
Thank you. Are there questions for Andreas?
Hi, Andreas. How flexible is your code with respect to changing things like the type of boundary conditions, or perhaps adding things like time dependence to the boundary conditions? Would these be things that could be easily included?
Yeah, that's a very good point. So at the moment,